Going back to what we have with subspaces and orthogonal subspaces, now we have for this part what are regarded as fundamental subspaces of a matrix. And we have four fundamental subspaces of a given matrix A, and they are listed as follows. And we have with the symbolism, so we have N of A is equal to the null space of A, and R of A is equal to the column space of A. And it's been a while since we've looked into column space, and I'll provide a bit of a refresher on that. And for N of the transverse of A, that's going to be the null space of the transverse of A. And for R of the transverse of A, that's going to be in reference to the column space of the transverse of A. And for the relations we have among these four fundamental subspaces, we're going to have that if A is an M by N matrix, then R of A and N of the transverse of A are going to be orthogonal to each other inside Rm. And we have R of the transverse of A and N of A, they're going to be orthogonal in Rn. And we have for the direct sums between R of A and N of the transverse of A, that is going to be equal to Rm. And we have for R of the transverse of A in the direct sum with N of A, that is going to be equal to Rn. And just taking what we have and looking at these four fundamental subspaces of matrix A, and let's say that if we have A to be a 4 by 3 matrix, where we have the top row we have 1, 2, 3, next we have 4, 5, 6, followed by 7, 8, 9, and the bottom row we'll just say we have 0, 0, and 0. And if we're looking at the null space of A, okay, so you have, again, so the null space of A, we have N of A, and looking at the null space of A, so I'm looking at taking A times the null space, or I should say, yeah, the null space U is equal to 0, and just putting this already in augmented matrix terms. Okay, so going row by row, so I have 1, 2, 3, 0, 4, 5, 6, 0, 7, 8, 9, 0, and I have zeros across, and displaying in reduced row echelon form. Okay, so I have 1, 2, 3, 0 is transformed to 1, 0, negative 1, 0, and this will lead up to the relation where we have that x of 1 is equal to x of 3. And for the second row, inside the reduced row echelon form matrix, we have 0, 1, 2, 0, and this is going to translate to where we have x of 2 is equal to negative 2 times x of 3. And I see there's nothing that we have in terms of x of 3 or x anything else. So x of 3 is going to be a free variable, and we can say that x of 3 is equal to t. And if that is the case, well, x of 1 is also going to be equal to t. And with x of 2 equal to negative 2 times x of 3, we have in terms of t, x of 2 is equal to negative 2t. So the null space, again, we have the matrix consists of x of 1, x of 2, and x of 3, and going ahead and factoring out t based on the relation that we have among the three variables, we have t times the matrix consisting of 1, negative 2, and 1. And that vector is going to be the key factor in determining the basis of the null space, and that is going to be the set consisting of negative 1, or I should say 1, negative 2, and 1. So N of A is going to be equal to the span of the set consisting of 1, negative 2, and 1. Now, in terms of what we have for the null space of the transverse of A. Now, the transverse of A, okay, you have in this arrangement, we have a 3 by 4 matrix. So you have 1, 4, 7, 0, 2, 5, 8, 0, and 3, 6, 9, 0. And, okay, so you got the transverse of A times the null space, represented by U is equal to 0. And putting what we have in the augmented matrix, okay, so you have 1, 4, 7, 0, 0, 2, 5, 8, 0, 0, 3, 6, 9, 0, 0. And for the reduced row echelon form, okay, so the top row we have 1, 0, negative 1, 0, 0. And in terms of the relation, we're going to have that x of 1 is equal to x of 3. And the second row we have 0, 1, 2, 0, 0. And the 1 is in reference to x of 2. And if I move 2 on the other side, say, of the hypothetical equation, we're going to have negative 2 times x of 3. And x of 3 is a free variable. And guess what? X of 4 is also a free variable. So for the null space, okay, you have consisting of x of 1, x of 2, x of 3, and x of 4. And for what we have lined up, okay, with x of 3 and x of 4 as free variables, we have x of 4 equal to t, x of 3 is equal to s, and from the relation, we're going to have the x of 2 is equal to negative 2 times s, and x of 1 is equal to s. And so in terms of the variables s and t, so we have with the 4 by 1 matrix, okay, as we proceed and look at what we have in the translation as we go down from x of 1 to x of 4. So I have s, negative 2s, s, and t, and partitioning out the vectors, okay, with the variables s apart from that which has t. Okay, so we're going to have s times 1, negative 2, 1, and 0, and I have plus t times 0, 0, 0, and 1. So I have a t term for x of 1, x of 2, or x of 3, only for x of 4. And the basis for the null space will be the set consisting of these numerical vectors, namely where we have the set of the 4 by 1 vectors, first of which we have 1, negative 2, 1, 0, and the second we have it 0, 0, 0, and 1. And from this, okay, we're going to have that the n of the transverse of A, again, which would be the null space of the transverse of A, that is going to be the span of the set consisting of those two numerical vectors. Now, in the crossover to what we have with column space, and going back to A, all right, so we're looking at the column space of A, which we have R of A, and looking at what this is going to be, and just kind of going back chapters ago. Now, the basis for the column space of A is going to be the basis for the row space of the transverse of A. Now, for the transverse of A, again, you have the same 3 by 4 matrix from earlier where we have 1, 4, 7, 0, 2, 5, 8, 0, 3, 6, 9, 0, and putting what we have in terms of not reduced row echelon form, but row echelon form. And so taking twice the first row elements away from the second row and 3 times the first row elements away from the last row. So we have 1, 4, 7, 0, 0, negative 3, negative 6, 0, and 0, negative 6, negative 12, 0. And to convert the negative 3 in the second row to 1, I'm going to take negative 1/3 of the second row. So we have in the rewrite, we have 1, 4, 7, 0, 0, 1, 2, 0, 0, negative 6, negative 12, 0, and I can get rid of the negative 6 upon taking the last row elements and adding to it 6 times the second row. And guess what? We're going to have negative 6 plus 6 cancels, and negative 12 plus what's going to be 12 is also going to cancel. So we're going to have for the row echelon form, we have the top row at 1, 4, 7, 0, middle row at 0, 1, 2, 0, and the last row is 0. So we have W sub 1 with 1, 4, 7, 0 and W sub 2 at 0, 1, 2, 0. Those will form a basis for the row space of the transverse of A, and also will form a basis for the column space of matrix A itself. So the basis for the column space of A, and if we arrange the numbers vertically, okay, so we're going to have spinning off from W sub 1, we had the vector consisting of 1, 4, 7, 0, and W sub 2. We had the column vector consisting of 0, 1, 2, 0, and the basis is going to be that set. And for the column space of A itself, it'll be the span of that entire set. And note, okay, both R of A, the column space of A, and we had the null space of the transverse of A, those are going to be orthogonal to each other. And we have finally, now looking for the column space of the transverse of A, and just sort of inverting the language from the immediately prior example. Now we're going to have that the basis for the column space of the transverse of A is going to be the basis for the row space of A itself. So putting things back in terms of A with 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0, 0, 0. If we arrange this and get to the row echelon form, so I have converting the 4 and the 7 to zeros. So from the second row, I'm going to take away 4 times the first row elements, and with the third row, I'm going to take away 7 times the first row elements. So we have in the rewrite 1, 2, 3, 0, -3, -6, 0, -6, -12, and once again we have triple 0. And then converting once again the -3 to a 1, I'm going to take -1/3 of the second row. So the second row becomes 0, 1, 2. And getting rid of the -6 immediately below the 1, we're going to have another scenario of where we are taking the third row and adding 6 times the second row. And so we're going to have another 0 row. And so the non-negligible portions we're going to have with the top row where we have W sub 1 consisting of 1, 2, 3. And then we have with the second row we have W sub 2 with 0, 1, and 2. And those will form a basis for the row space of what we have for the transversal of A. And so for what we have in this particular case, right, so we have form a basis for the transversal of A. And the basis for the column space of A, again, arranging what we have vertically, so you have vector with 1, 2, 3, and also with 0, 1, and 2. And for the column space of the transverse of A, that is going to be the span of the entire set. And once again, the null space of A and the column space of the transversal of A are going to be orthogonal to each other.